In this part of our electrochemical cell lab, we're going to be utilizing the Nernst equation, which allows us to calculate the voltage of a cell for non-standard conditions. The Nernst equation itself utilizes this particular format, where we have our E with the degree sign represents our standard conditions voltage, which would be when we have 1 molar concentrations. Our E without the degree sign would be what our voltage would be when the conditions are something other than standard conditions. The E degree sign, standard conditions, specifically means that this would be our voltage when we have conditions of 25 degrees Celsius, 1 atmosphere pressure, and all aqueous solutions have a concentration of 1 molar. Our E without the degree sign would represent when the conditions are anything other than standard conditions. If we were to have aqueous concentrations of something other than 1 molar, we'd be operating under non-standard conditions. In the Nernst equation, the value for R is our gas constant utilizing energy units, so it's 8.31 joules per Kelvin mole. If we run at 25 degrees Celsius, our temperature is going to be 298 Kelvin. The value of F in the Nernst equation represents something known as Faraday's constant. Faraday's constant is the charge which is measured in coulombs on 1 mole of electrons. Faraday's constant is 9.648 times 10 to the 4th coulombs per mole of electrons. One thing we can do to streamline the Nernst equation is if we're operating under essentially room temperature conditions, our values for RT divided by F will always be a constant. We can lump these together to create a single constant. Putting everything together, our R times T over F, multiplying and dividing out, we get a value of 0.0257 for R, T, and F combined together. This allows us to rewrite the Nernst equation. In our streamlined version, we've substituted in 0.0257 for the combination of R, T, and F. Since those are all constants, we can utilize a single constant to represent all three. In the Nernst equation, N represents the number of electrons that are transferred once we've balanced the number of electrons being gained and lost in our oxidation and reduction half reactions. This would be our value for N. Our value for Q is known as our reaction quotient, which is set up the same as an equilibrium constant, except when it's Q it would represent non-equilibrium values for the concentrations present. Let's run through a sample calculation using the Nernst equation. Let's just pick 2 half reactions. Our GUR half reaction will be the reduction of gold ions to elemental gold, and the LEO half reaction is going to be the oxidation of magnesium solid to magnesium ions. Our first order of business, let's make sure we have the number of electrons being gained and lost balanced. We'll have to multiply the first half reaction by 2, and we'll multiply the second one by 3, which will give us 6 electrons being gained in the reduction, along with 6 electrons being lost in the oxidation half reaction. When we go to use the Nernst equation now, because the number of electrons being gained and lost is 6, our value for N for this particular combination of half reactions would be 6, as the N in the Nernst equation represents the number of electrons being gained and lost once we have the equation balanced. Combining the 2 half reaction gives us our overall balanced equation, and also gives us a positive voltage, positive 3.87. This is our E cell, specifically for conditions when it's standard. Standard conditions would tell us that all aqueous materials, the Au3 plus ions on the reactant side and the Mg2 plus ions on the product side, would both have to be 1 molar to give us our E cell of a positive 3.87 volts for this electrochemical reaction. Conceptually, as the concentration of the reactant would drop less than standard conditions, that would cause the rate of the reaction in the forward direction to become slower. Additionally, if the concentration of the product builds up at the same time, that would also inhibit the reaction going in the forward direction. As the rate in the forward direction would go slower, the voltage of the cell would actually drop. This is what happens over time as the reactants in an electrochemical cell get consumed and turn into product. The reactant concentration goes down, product concentration builds up, the voltage drops. Eventually the voltage drops to where it's equal to zero, and that's at a point where we would say that the battery is dead. It's no longer usable. It's also indicative when we hit a voltage of zero that the system is at equilibrium, where the rate forward and rate in reverse directions are equal. And under those conditions, the battery will no longer produce any voltage. On the other hand, if the reactant concentration were to increase above standard conditions, this would cause the rate of the reaction in the forward direction to go up, which would also cause then the voltage of the reaction to increase. So a way to get a higher voltage than what we have for standard conditions would be to make the reactant concentration higher than standard, and if at the same time we drop the product concentration below standard, that'll encourage the reaction to proceed in the forward direction, causing our voltage for the cell to actually be higher than standard. Let's do a couple sample calculations with the Nernst equation using this balanced electrochemical cell reaction. Let's start with non-standard conditions where our reactant concentration is 5 molar, and let's just, for the sake of our example, make the product concentration 0.10 molar. Let's also set up our expression for Q, the reaction quotient, keeping in mind that when we set up an equilibrium constant expression, solid phases drop out of the expression, aqueous phases remain in the expression. The expression is also a ratio of product divided by reactant. For this particular reaction, our expression for Q would be the magnesium concentration cubed because we have the coefficient of 3, and then also divided by the gold concentration, which is our reactant, and that's raised to the second power because of our balanced equation coefficient of 2. Let's put our information into the Nernst equation to now calculate what our voltage would be for non-standard conditions. Now remember, we determined earlier our value for N was 6 because we had 6 electrons being transferred when we balanced our two half reactions to create our overall electrochemical reaction. So putting in our expression for Q, we have our magnesium concentration cubed over the gold concentration squared. We'll put in our non-standard concentrations of each of these into our expression for Q. For our current conditions, this would now be our setup of the Nernst equation to determine what our voltage should be for these non-standard conditions. Before calculating, because we noticed that the reactant concentration is greater than standard conditions and the product concentration is smaller than standard conditions, this is going to drive the reaction forward to a greater degree, which would cause our voltage to increase above and beyond what we would see for standard conditions. Calculating a value for E, we find that our new voltage would be 3.91, an increase above and beyond what we would see for standard conditions, which would be expected considering that our reactant concentration is greater than 1 molar and our product concentration is lesser than 1 molar. Let's change our reaction conditions now and make the reactant concentration low, 0.10 molar. Let's make our product concentration high, 5.0 molar. Under these conditions, we would expect the voltage to drop lower than standard conditions because we have a low concentration of reactant, which would cause the rate in the forward direction to slow down, and the buildup of our product concentration inhibits the reaction in the forward direction. This would be what's happening as a battery runs its course. Reactant gets consumed, turns into product, the voltage over time will drop. Again, we have our Q expression, which is our magnesium or product concentration cubed, divided by our reactant concentration, the gold ion, squared. Once again, our value for N is 6 because we had 6 electrons being traded in the reaction when we balanced it to make sure the number of electrons gained and lost were equal in the equation. Putting our reactant and product concentrations into our Q expression, we can now calculate what our new E value would be for these non-standard conditions. Calculating E, we find it to be 3.83 volts, which is lesser than standard conditions, so our voltage has dropped, which would be reflected by what we would expect with a low reactant concentration and a high product concentration. Now eventually an electrochemical cell we can reach the point where the rate in the forward direction becomes equal to the rate in the reverse direction. Under these conditions, we would say the reaction is now at equilibrium. When the reaction reaches equilibrium, our E value for non-standard conditions becomes equal to 0. In that we have the reaction proceeding forward and in the reverse directions at the exact same rate. Consequently, the amount of voltage generated would be nothing. The Nernst equation itself would change then to reflect this, and that when we're at equilibrium, we'd no longer have a reaction quotient, but we'd have what we would say is K, our equilibrium constant, if the conditions are for equilibrium. So the Nernst equation, our non-standard voltage becomes 0, and instead of Q, we now have K in our expression to reflect that we're now at equilibrium. Rearranging, we can now have the Nernst equation for at equilibrium, where we can solve for our equilibrium constant. Now, one thing for electrochemical cells, it's not unusual to have equilibrium constants that can be something times 10 to the 50 or times 10 to the 125, very large exponents, which indicate that the reaction proceeds predominantly and almost exclusively in the forward direction. So extraordinarily large equilibrium constants for spontaneous electrochemical cells is not only not unusual, but it's to be expected since these reactions proceed to such a degree in the forward direction.